competitive enough around the global market to serve the nation as well as the society global. So with this, I will take you the technology deep dive so that it will be beneficial for us to understand what are the difference, what are the technologies, what are the different domains of the technologies, and what are the areas where the challenge has to be overcome. You can buy one technology, my dear friend, as a technology partner, but you will not learn the nitty and gritty of that technology. Without knowing the nitty and gritty, you cannot run. It is nothing like I went to a car shop, buy a car, having a tutor how to drive a car, and I can roll down the car. This is nothing like that, not so simple. Even somebody teach me how to run the technology, how to manufacture that. I also need to know what is the troubleshooting mechanism. Okay, why is it so? I will let you into the slides. Let's go. It's an open house discussion. Anytime if you feel bored, please stop me. We can crack jokes out here. Try to make best use of the time, okay? And if any questions, you can ask at any stage. If I am knowing, definitely I will come back to you. If I am not having the answer at this moment, I will get back to you. So what has been painted with the semiconductor technologies? As we know, everything around us is gone by the semiconductor. And without semiconductor, even your AI doesn't work. So even your communication system doesn't work. Even your education system doesn't work. Even your day-to-day digital communication, digital payment gateways, nothing works. Your healthcare, your transportation, your communication, everything seized off. So, whomsoever is having a leadership onto the technology on semiconductor manufacturing hardware would be at the top of the world. And who is at the top of the world? Anybody? Taiwan in terms of manufacturing, my dear friend, I agree with you. But in the technology and IP holding, हाँ? अभी थोड़े दिन पहले न्यूज़ में था यार बहुत. NVIDIA of US, and United States is having a holding of IPs more than 95%. They are the leader. Why China is struggling? Because of not having the IP at all. But however, they have made a policy in such a way, my dear friend, to develop a holistic ecosystem, and they have started in 1999, and by now they are a big threat to the world. They have developed by the technology by themselves, by hook or crook. That need not to mention, you know the underlines. Okay, so that's why they are the leader right now, and they have competed. Over the last 30 years, I will have put two slides here. One is particularly, I think it is not working. Okay, no issue. Last 30 years, the technology was based on interconnecting the people. And next 30 years, it is going to interconnect your infrastructure in and around the world to you. You have the AI, you have the Google, you have the Gmail, everything is available. You ask any questions, they will answer to you. Ask good questions, not the bad one. You will get the answer for both. Grok, you know. Semiconductor revolution, past and future. Okay, you see the technology nodes, which is maturing right from 130 nanometer. It is very, very old technology though, but from there we have started. The world has started at 10 nanometer, 10 micron, not nanometer. 10 micron, then 8 micron, then 5 micron, then 1.2 micron, then 0.8 micron, and SCL 0.18 micron, very good, and 180 nanometer. Okay, and the world is sitting here in this domain. Then you have 65 to 10 nanometer. The application segment is IoTs. Of the technology nodes, say 130 to 28 nanometer. Then we have 65 to 10 nanometer of technology nodes, where application segment is mobile, and the third one 65 to 14, even up to say latest 3 nanometer, we have high performance computing. This is how technology has ruled in the different segment of the devices. Okay, I would say devices, ICs. Okay, it's not a discrete. take this as a, and then what is the difference out there? If you see processing at 180 nanometer, which is the only fab in India we do have right now, which is operational, it is having 450 processing steps before the wafer goes out. Means a designer do the designing using the PDK of 180 nanometer, which you might be learning here, my dear friend, and then you do the tape out based on the PDK provided by a foundry, which is, let us say, SCL. And after that, it is turned out into a mask, and then mask goes to the fabrication. And it took 450 steps before the device come out, means the wafer come out, not device even. And then you do the ET, electric test, seeing whether the process which you have done over this wafer, all 450 are in sync together. If they are not in sync, at one process fails, everything fails. This is what the criticality is, and what is called sigma control of a process. So the process control requirement is up to 3 sigma. What does this mean? The student who has done the statics, they know what does this mean. And the best post-process technology is 6 sigma process control. Automotive manufacturing, the manufacturing for the Boeing jet engines, Boeing engines required 6 sigma control. Semiconductor manufacturing required 3 sigma to 5 sigma control for the process. This is only the way to understand in a broader terms for this. And even at 3 sigma, a single failure into the process will cost you the yield loss, number 1. It will cost you the loss of your dollars per unit area into the real silicon real estate. I'm not talking about the land real estate. I'm talking about silicon real estate. That will be costing you. And the next is, if I'm going to 65, my dear friends, 625 processing step has to be in sync. And at 5 nanometer, almost 1800 processing step. Out of 1800 processing step, if 1 or 2 process steps goes bad, whole lot is washed out. You are making petty loss. Your time loss, your money loss, your infrastructure as well as your raw material got lost without giving a penny to you. So that's the risk. And even at the ET itself, if any is mismatch in these processes itself, my dear friend, there's a big ask. Okay, you cannot find out the problem. If you are not smart enough to find out the problem in a process, then you're following lots which are running in the fab. They are also gone. So you know where is the fault. If you are not knowing where is the fault, what is the way to mitigate it, what is way to troubleshoot it, your fab is seized. Your whole money is lost. Whatsoever it is $4 billion or is a $5 billion, it's zero. Let me give you one example. The best example is, my dear friend, I'm sorry, I'm not coming to that side, I'm coming to this side now. The worst ever actually, the example is Panasonic fab. Panasonic put a fab in Japan by investing $6 billion in 1918. That was the fab which is based on a technology of 22 nanometers, which is a FinFET architecture of a CMOS transistor. We will discuss what are the FinFETs. You might have done studied in your curriculum also. Then they struggled for 5 years to make money out of it, make device out of this facility. Device means IC with a specific yield mark. That yield mark was at least 80% to start with. They were struggling from 22 to 40%. 5 years they spent, then they closed the fab. And in 5 years they burned around another $2 billion to scale up the process. Though they are the master in the technology, but they were not able to troubleshoot this. That's where the point came. If we do not understand the technology right from the scratch, we cannot run the fab, even by copying the technology from somebody. So our smartness has to be in that domain that we understood every nitty-gritty of the process and technology which we are absorbing, number one, or which we are developing, number two, or which is mastered by ourselves right from the scratch to the final product into the market, number three. So this is the only three ways where we can success ourselves. Otherwise, no chance in this business. A big risk. So let's go to the next. I am not sure. Okay, that is also there. Okay. Now this is particularly for an information slide, where when we talked about the semiconductor revolution technology roadmap, which is right from starting, I have taken to 28 nanometers. It's a quite advanced technology so far as the commercial utilization of the technologies are concerned. Then we have 20 to 3.5 nanometer. You see the transistor structure. Just have a look onto this. The planar structure goes up to 22 nanometer. Then it comes to the 2.5D, 3D structures, which is FinFET architecture. And in FinFET architecture is also there is a different architecture of the transistor, which we are going to discuss here today. Apart from that, the metal layers and the metal material, although right from 28 nanometer to say 3.5 nanometer, the interconnecting metals, they remain the same. It's a copper, tantalum and tantalum nitride. However, on the last end, we have seen copper, ruthenium and tantalum nitride is the material which is material of choice to do the interconnect between the metal. And now again, one part, stress and strain. See, this is what exactly the definition where we are struggling with the technologies. People are struggling with the technology. The people who are not having access to the technologies, they are struggling with these factors. We'll go to the next one. Now, just to give a comparison with what we have discussed in the previous slide, size of the same integrated circuit at 45 nanometer, at 32 nanometer, at 20 nanometer, at 14 nanometer, at 10 and up to 18 angstrom, which is not in production but tape out is there. Let us focus on 3 nanometer. The size is reduced, and what else is getting benefited? What else is getting benefited? Power, my dear friend. Because when you are going to the market, every system is battery operated, is power hungry. You need, what is the battery life? Battery life, who is the deciding factor? Is your gadget is deciding factor? No. These are the deciding factors. How much power hungry they are, they will be deciding. However fast computing they are doing, they will be the deciding factor. You must few of the design engineer who have done the layouting, routing and analysis. What you are focused on the figure of merit of your complete structure design. And what are the three parameters? Power, area and performance. Only three parameters you focus on. Based on this, you get the simulation result, or you decide whether your structure for a certain technology node is giving the optimum performance. That is on the CAD tool, not onto the silicon. And you go, okay, thumbs up, everything is okay, we can go for the DRCs. And you go for the DRC, when DRC is done, you say, okay, it's done, I can do the netlist and layout and floor planning, and we can tape out it. You do the tape out, and once the tape out is being done, then rest depends on the fab to run the total mask until the whole structure is sculpted onto the silicon to give the complete device structure to you guys in your hand. Anything fails means we are failed. So that's what the difference. So मैं पूछना चाहूंगा, कुछ अच्छा हो रहा है, सीखने को मिल रहा है, बुक से बाहर है, बोर हो रहे हूं तो बता देना यार. मेरे को हरियाणवी जोक बहुत अच्छे आते हैं. I'm good at those. Okay, so where we are and where we need to go. Just focus. This is the planar structure. जिस बच्चों ने पढ़ा है CMOS, उनको पता होगा. नहीं पढ़ा है वो समझ लो planar structure क्या है. And what is the next structure which is for the advanced? It is also planar, which I have given you in 2 dimensions only. The first one is silicon substrate having source and drain. There are the 3 or 4 terminal device you can say, and we have a gate, we have source, drain and a channel. It may be N-type and P-type device. Then we have another technology, metal gate, where high K gate dielectric is used, and we have the same structure, source, drain and channel, and with one gate. Here the gate is polysilicon, here the gate is metal. And if I go back, metal start right from 45 again. Earlier, metal was there up to 1.2 micron technology, metal as a gate, which is aluminium metal is used as a gate, then aluminium replaced by polysilicon as a gate. Might have studied in your curriculum. Why it was so? Give me answer. Again we come to the metal. So say 1.2 micron to 45 micron technology, we were using polysilicon as a gate, whereas at again 45 to n number of technologies, let us say 18 angstrom, which is in R&D right now, we are using metal as a gate. Either it is for N or is a P device. Both we are doing the metal as a gate. Why is it so? I'll leave with you. If anybody would like to answer, he or she can answer. Okay, leave it. We'll come to this problem later, briefly. Now, focus. This is what? Anybody can tell what is this? This is a SEM image of a real transistor, CMOS device. It's a real SEM image having the gate structure, my dear friend. I think this is not working. Let me go there. This is the gate, and this is your gate oxide. And this is our source, this is our drain, and this is what the channel is in between. And what are the technology challenges when we are shrinking the device? The technology challenges has been told here particularly in all these four graphs, sorry. We have band-to-band tunneling because of the shrinking nature of the device. You are reducing the channel length, you are reducing the width, you are reducing the thickness of the gate oxide. You have the band-to-band tunneling. You have the band-to-band tunneling from the this to this, this to this, and this to this, and this to this also. Okay? And you have the gate tunneling, gate to the channel, gate to the source, and gate to the drain. You have the tunneling from source to drain tunneling. Since the channel length is very small, there's a possibility if field level is high, drain induced barrier lowering. You might have studied in your curriculum, which is responsible for, going the leakage from the source to the drain region. And then we do have the quantum confinement. There may be a trap charge in between at the oxide or interlayered dielectric material which are used to interconnect the device from the front end to the back end. And that creates a problem. What kind of a problem? Leakages. If leakages are more in your transistor, your power consumption will be more. Maybe you can survive with the noise margin when you are utilizing this transistor for digital application. Not for the analog, not for the mixed signal, and not for the memories. Okay? So, we have to handle all these problems while we are scaling the device. This remains a technological challenge at every node, even if you talk SCL at 180 nanometer, if you talk at today, TSMC has 3 nanometer, Intel at 18 angstrom. Remain the same though. Architecture is changing, problem level remains the same. We have to address all these problems to solve the technological issues. But these are on the front end of the line only, not the back end. अभी हमने बात की है जहां हम ट्रांजिस्टर बना रहे हैं, हमने वहां बात नहीं की जहां ट्रांजिस्टर को आपस में रिकनेक्ट कर रहे हैं to make the integrated circuit. You have to understand that part. Okay, so I leave it here, and where we are going. So at present, say up to 28 nanometer or 22 nanometer, we are at the planar technology in 2 dimension. Whereas 22 nanometer and beyond, we are going 3 dimension, which is a FinFET or tri-gate technologies. So fin is something like fin, and then fin is covering all this. And why this happens so, I'll let you know. The technologies. The technologies so far as which we have discussed, they are defined by the technology node, which is defining how close device you can place, my dear friend. But it is also defined whether the nomenclature remain the same for the technology node. No, it is not so. Earlier it was say, okay, how close source and drain are being placed. Based on the gate length, you define the technology node. But there are some stage where not the gate length for first metal layer, the center to center pitch is defining, center to center pitch is defining the technology node. Then we enter into the 3D domain. And 3D domain, no nomenclature works. Only architecture works. I can't define what the minimum pitch of line I am drawing. Of course, that is there, which is playing the role because it is geometrical dependent structures, which we have to print onto the silicon straight away. And if you are not printing onto the silicon, there's a media for this, which is lithography machines. So lithography machines is supposed to be, जैसे हम अभी X-ray analog when we used to click the photos with the analog camera having a reel, you click it, image is formed on the negative and the negative is developed. Similar way is the microelectronics works, my dear friend. You might have read in your curriculum. The lithography is the process which is translating the information which is given by the design engineer in the form of a mask, from the mask to the substrate. That's what I am doing the imaging. And what is the limitation? Is the light. How close you can resolve to feature. Relay criteria, how close you do the feature. And if I'm putting the dimensions so close, where we are talking about 10 nanometer, 5 nanometer, 3 nanometer, or say 1.2 nanometer or 18 angstrom, you can understand, my dear friend, where is the light? Is light have sufficient wavelength? Is that can resolve these features up to that level? What is the technology associated which can print this? My two friends are laughing. So बताइए, what is the relay criteria? Relay criteria. लाइट देखिए, लाइट का वेवलेंथ है. आपसे पूछ रहे हैं मित्र, हम सो रहे थे ना, थोड़ा जाग लेते. वो भाई भी सो रहा पीछे, कोई बात नहीं. लाइट की वेवलेंथ का पता है? नहीं पता, कोई बात नहीं, थोड़ी देर में पता लग जाएगा. अंदर से भी आएगी, बाहर से भी आएगी. ठीक है. सो बेसिकली वेयर वी आर गोइंग, राइट फ्रॉम द प्लेनर टू द ट्राइगेट, माय डियर फ्रेंड. एंड द टेक्नोलॉजी वाइज व्हाट वी आर सेइंग दैट वी आर डूइंग हैलो इम्प्लांट टू द वर्टिकल ऑल अराउंड स्ट्रक्चर्स. मींस द डिवाइस स्ट्रक्चर इज चेंजिंग. And if device structure is changing, the technology is changing. So, and let's go to the technological challenges. We have different material, different solution nowadays. अब क्वेश्चन फिर आपसे है, my dear friend. अब आप बताएंगे दोस्त. फास्ट चार्जर्स अवेलेबल हैं, आप यूज करते होंगे. यू आर एप्लीकेशन इंजीनियर, आई नो. यू नो फास्ट चार्जर्स फॉर लैपटॉप्स, मोबाइल्स. अर्लियर चार्जर वर वेरी स्लो. 8 घंटे लगाना पड़ता था, तब मोबाइल चार्ज होता था. क्या डिफरेंस है? क्या कह रहे हैं? नहीं सर, कुछ और बताइए. कुछ और डिफरेंस है क्या? आप मार्केट में फास्ट चार्जर लेने चले गए, कुछ पूछा दुकानदार से आपने? है? क्या पूछा? वॉटेज पूछा. वेरी गुड, आई लाइक इट. आपने वॉटेज तो पूछा कम से कम. क्यों पूछा वॉटेज? Yes, very good. But whether the technology is same, which is silicon, can handle those wattage. एनर्जी बैंड डायग्राम कितना है? अगर हम कंडक्शन बैंड टू वैलेंस बैंड सिलिकॉन का बैंड गैप देखें, वो कितना है? बता पाएगा कोई? कोई बताए? फिर तो हमने सेमीकंडक्टर पढ़ा ही नहीं यार. Then I am wasting my time. Energy band gap for silicon 0.7 क्या यूनिट? इलेक्ट्रॉन वोल्ट. चलो मैं थोड़ा सा मान लेता हूं, वैसे मैं कन्विंस्ड नहीं हूं इस आंसर से. सो वो क्या ऐसा है चीज, माय डियर फ्रेंड, जो ब्लॉक कर देती है वोल्टेज को? कोई लिमिटेशन है? अब जैसे when we are using the ICs, my dear friend, we are talking about the voltage at 1.2 volt, 0.8 volt, 0.5 volt, 0.6 volt to reduce the power rails while you are designing your circuits. But the voltage which maximum can be blocked is decided by the band gap of the semiconductor. That's what, my dear friend, fast chargers. Their material is different. It is not silicon there. That's why this slide is very important. You need to understand, my dear friend, we have the options in silicon. We have the options in gallium arsenide. We have the option in silicon carbide. We have the option GaN on silicon. Now, जब दोबारा फास्ट चार्जर लेने जाओ, GaN चार्जर लेके आ रहे हो तुम, ये बता रहा हूं मैं, ठीक है? और e-vehicle has revolutionized everything now. महिंद्रा की कार तो सबकी फैंटेसी कार होगी, साइबर ट्रक, EV9, good one. But what the technology behind, my dear friend, is the semiconductor. And which part? Silicon carbide, silicon, as well as GaN. All three technologies are being utilized. Fast charger for the cars is based on silicon carbide technology. PMIC, power module integrated circuit in that car to supply the chain of the power to the different electronic gadget is based on the GaN ICs. And rest processing is MPFI, is silicon technology. Now, you understood everything. Okay, that's why we need to address all these technologies. Not the single technology can provide us the solution. All the technologies we have to focus to provide the solution. However, basic platform remain the same. The manufacturing platform. It's only the design environment change, the physical property change, the process technology may remain the same, but however with some tweaking you can control that. The complexity also altogether may be less as compared to CMOS technologies, where the integration level is so high as compared to the discrete device. If we are using SiC, if we are using GaN on silicon, but integration level again is complex. Let's go to the next one. Scaling. What is the CMOS? CMOS we know now by this form. And what are the main parameters? The switching speed. While we are scaling the device, only the three factors we need to take into account, my dear friend. Mostly power, area, performance. Again, I am saying that. Performance depending upon the switching. I on as well as I off. They depend upon the area and of course the structure of the device and the voltages at which it is working. The performance, area and power. As I am shrinking the device per unit area, reducing the power rails to handle that transistor, I am playing with the power, reducing the power. What figure of merit we are drawing out of it? We are drawing the three figure of merit of it. Go with this. Size, every technology node, we are reducing 7x time. 0.7x, sorry. Then performance cost 30%. Then you have power reduction by 5%. Area gain 50%, cost reduction 35%. That is the power of scaling and that is the power and zeal of integration. Why? Can we stop somewhere? Light is the limitation. Light, wavelength. याद रखना हम अंत तक नहीं छोड़ेंगे वेवलेंथ को, ठीक है? इश्यू क्या है माय डियर फ्रेंड? इश्यू ये है superior short channel controlling is the crucial since sets boundaries, particularly if device is not switching on or switching off, it is no use. If it is leaky, it is no use. These are the challenges. So I classified in a simple way technology challenges at irrespective of the technology node in two aspects, front end of the line and back end of the line. FEUL, front end of the line, BEUL, back end of the line. Can anybody tell me what is FEUL, what is BEUL? I'll give 500 rupees right away right now. 1000. एक पेन, अच्छा पेन सबसे पावरफुल चीज है. चलो कोई बात नहीं दोस्त, हम सीख सकते हैं इसको. फ्रंट एंड ऑफ द लाइन होती है फैब्रिकेशन टर्मिनोलॉजी used by the design engineer as well as the fab engineer when they are discussing together. Front end of the line is where the transistor is being formed. जो मैंने structure what I have shown you, I have told you there, I am talking about the front end of the line. Means when the source drain is formed, where the gate is formed, my dear, where channel is formed. That is front end of the line. When it is connecting to the rest of the transistors by metal lines, okay, whether it is 1 layer metal or 11 layer metal, that is back end of the line. So this is the segregation. When interconnect devices are being manufactured without interconnecting together, that is front end of the line. When it is interconnecting together, that is the back end of the lines. Okay, these are the two terminologies, and these are the problems even. These two lines gives us challenges: short channel effects, interconnect delays due to the RCs. RC, you know, RLC or RC, ठीक है. So मैं इसको अभी छोड़ देता हूं क्योंकि मुझे टेक्नोलॉजी ज्यादा बताना है. So all these two things are very crucial. Short channel means if the transistor remains on always. Since we are shrinking the dimension, the distance between source and drain, just physical समझो, the distance between source and drain is so narrow that without applying a gate voltage, you may have a channel exist. You may have a possibility of carrier transportation, tunneling from source to drain, gate to source, जो tunneling impact मैंने बताया था, वो they can happen, and your transistor may remain on and is consuming power without even in static or dynamic mode. In static mode itself, dynamic mode it's supposed to consume the power, but since there are millions of transistors per unit area, they are not functioning at tandem at one time. There might be few transistors which are working for certain 10 seconds, which are working another 10 seconds. They should remain off to maintain the power best use of your ICs. That is the clock sequencing you might have heard while you are designing. Okay, so which we decide which transistor is supposed to be, and then this is controlled by the RCs back end, the sequence control, and the front end is decided by shrinking the dimension if the transistor remains on without mitigating the issues of short channel. It is only one thing which I have talked. Another thing, mobility degradation. Switching speed directly depends upon the mobility, mu factor, which you have seen in the equation which I have shown in the previous slide. What mobility degradation is? If the channel is so short and it is impacted by the fields associated around it, whether it is gate field, it is source field, it is drain field, or it is substrate associated field, or any trap charge field, the mobility degrades a lot. Mobility for holes and electrons, creating problem for your switching will be low. Device performance ceased, not required. So these are the problems which we need to associate it. And where is the solution? You see particularly this graph which I have kept for the researchers always open is aluminium or versus SOI. Then we have copper versus low-K dielectric. If you see the switching speed, particularly the delays, when I am replacing the copper with the low-K dielectric material, the switching speed is faster as compared to when technology node shrink. If I am using the aluminum as a metal gate, the switching speed remain very, very high. Slow. Sorry, not high, it's slow. And if it is slow, there is no use of transistor. That's why aluminum at certain stage we have to rip it upon as a metal, as a interconnecting material. That's why the copper, the slide which I have given 28 nanometer to 3 nanometer and even 18 angstrom, not having the aluminum in that. We have only the copper. Aluminum serve the purpose of the RC delays as per the optimum design performance, even for a digital application or analog or a mixed signal. It will remain aluminum as a gate. Whereas then you have to go for the copper. अभी हम पॉलीसिलिकॉन और मेटल की तरफ नहीं पहुंचे 45 पे, अभी उसको अपने दिमाग में रखना थोड़ा सा आगे आ जाइए. टेक्नोलॉजी फ्रंट एंड एंड बैक एंड. मैं थोड़ा सा स्लो हूं, मैं थोड़ा सा इसको फास्ट खींचूंगा अभी क्योंकि टाइम परमिट है और मेरे पता है फोकस कितना हो सकता है. ठीक है, मुझे माफ करना, मैं थोड़ा सा स्किप करूंगा, फिर कभी कर लेंगे इसको, लेकिन मैं थोड़ा स्किप करूंगा. अभी सिर्फ आपको आइडिया दे रहा हूं. FUL and BUL interconnects. Okay, these are the technologies which is defining the short channel effect as well as interconnecting delays. Now, if we see what will be impacting, short channel effect will lose the gate control and go underline leakage of the current. Shallow extension of source and drain under the gate enable the recovery rate control. If I put extension under the gate, the structure which you have seen, I think it is feebly seen here. This is drain extension, this is source extension. We can cut down some of the drain-induced barrier lowering and also undesired leakage current in the off state. But if we keep on shrinking the dimension, this solution will not even work. Now there comes the stressor. This is okay for the short channel effect. But what about the mobility? You know the stress is inversely proportional to the mobility. यहाँ कैसे वो डायरेक्टली प्रोपोर्शनल आ गया? जितना स्ट्रेस बढ़ाओगे मोबिलिटी इंक्रीज हो जाएगी. अभी छोड़ दे रहा हूं मैं. 18% to 14% मोबिलिटी increase हो जाती है if we introduce stressors in between. And stressors we used to introduce in between the channel, even in the planar technology or in the fin technology. We used to introduce compressive stress or tensile stress. Compressive in case of PMOS device, tensile in case of NMOS device. Mobility increase 40% for the N channel transistors and 18 to 20% for the P channel transistors. So that's what the benefit of the stress used to give. It is not the scattering effect which are coming into the picture. It is because the size of the atom. This is the PMOS compressive, real picture of the device, semi-inch. This is 45 nanometer tensile silicon nitride layer having over it as a cap. And this is showing the tensile, which is enhancing the mobility of a N-type transistor. Now we need to avoid the tunneling. Sorry, another part. This I have skipped here for some time. And now another aspect, the gate oxide. Gate oxide particularly is silicon dioxide. And silicon dioxide is defining the what voltage, VT threshold is required to switch on the transistor. Silicon oxide is the ideal one. Up to 65 nanometer it was a good choice, because of its excellent property with the silicon and it's an easy growth property. But what after that? It is no more working for 45 nanometer and beyond. Then we have to do for the band gap engineering, back to the basics. We need high capacitance and the low K, high K and capacitance. And this particularly come up if I am having gate L silicon substrate and silicon oxide as a gate, or gate as a high K material as a oxide and silicon substrate as a gate. This is the structure which is around 45 nanometers and beyond. And if I am putting a stressor, this is not stressor, Fermi level. Now, if I am putting this with the polysilicon, what is the issue? Means I told you that we were at the metal gate at 1.2 micron, then left metal and pull poly as a gate. Then we come up at 45 again to the metal as a gate. These are the issues. When if I am using the poly, my dear friend, it is creating the fixed charge when poly is grown over the high K material, which is hafnium oxide. And the fixed charge, then remote phonon interface, interfacial dipole, if I am even replacing a small layer of silicon oxide layer, 1 nanometer, 1.2 nanometer here, still it is having a surface stage inbuilt charge and it creates a leakage path. And that leakage path is giving some leakages to the channel and even poly depletion effects. Means poly, due to the surface states here, remote surface roughness and fixed charge, is not having the sufficient voltage to make the channel inversion underneath the gate, which is called poly depletion. Means poly is not generating sufficient charge to pump into the channel between source and drain to make the device working. What will be the solution? Reduce the work function. It's not suit the poly. Go for the metal. Poly is having a high work function as compared to poly to SiO2 to the silicon. And if it is replaced by the metal with the hafnium oxide or SiO2, then silicon, it is having a lower work function. So I have a possibility that if I apply a small voltage, it can switch on the device immediately and it can work with this. That's why metal again come into the picture. Then why we have get rid of metal? It's up to you. This I have already discussed. I'll leave it. Stressors. I'm just showing the few of the structure. Now I'll focus few 5 minutes of yours here to tell you what the technology has been changed now. We have the planar technology, we have the FinFET, then we have gate all around, the latest architecture which is being utilized for the advanced technology now. So my dear friend, FinFET we know because of shrinking the size, channel is so close, जो source drain extension वो chop कर देंगे पूरे channel. So I can't afford that. There's no device at all. Even if I physically dimension are so close that it can be really replicate the transistor which we are making into the planar technology. It's not so then. If it is not so, then what will be the solution? Go into the fin. Control the channel underneath the gate from three sides. That's why the FinFET is. I am controlling the channel from three sides. Now, you can make source, you can make drain, and underneath is the channel. This is the FinFET structure. I reduce the dimensions. Then further, when we shrink the structure up to 7 nanometer, we go the gate all around. Still again, the problem remains the same, which has been defining for the planar technology, which has been defined for the FinFET technology. It remains the same again for that. Because channel again ceased. It's a losing control, gate losing control. How you can control? Okay, तीसरी side बस्ती है वहां से भी cover कर लो भाई इसको. Gate all around. Go for this architecture. Then we change again. Gate all around, whether in a single fin or double fin. At 5 nanometer. Go for 3 nanometer. Fin, nanosheet, fork sheet, and CFAT. At 20 angstrom. 1.2 micron, sorry, not micron, nanometer, galti मुझसे भी है. Okay, this is the PMOS, this is the NMOS, this is complementary FAT. So having gate all around in the same plane with the NMOS and PMOS device. However, here fin is departing between the PMOS and NMOS structures. Having 3 gate to control one transistor, having 3 gate to control one transistor, that's the difference. Only single transistor cannot. Then there's another stuff come into the picture. I'm skipping some of the slide. Now, we cannot interconnect at the back end of the line from the front side of the device when we are talking about geometrical structures which are 7 nanometer. They are, मुझे माफ करना दोस्तों मैं उधर नहीं आया, अभी आ जाता हूँ. They are, means, as we told that the front end side, it is coming from the top. Okay, if it is coming from the top, all metal interconnects at the back end of the line. I can go up to 10 metal layer or 11 metal layer. But RC delay, as I told you, is a problem. More is the thickness of the metal layers, RC delay will be more. Signal will lose itself while it is pulling out from the front end. In order to avoid that architecture change, we go for BPRs, buried power rails. Mean power is being transmitted to the transistor both from the back side and from the front side. And if you go to the next, the architecture nowadays is this, the transistor. Can you imagine? This is a transistor PMOS and NMOS. Having vertical fin, 3-dimensional structures. Where is NMOS, my dear friend? This is your PMOS, PFAT, and this is your NFAT. This is your channel region. This is source, this is drain. This is source, this is drain, and rest underneath is the channel which is having the gate all around. We have 2 fork sheath architecture. One P channel is at the bottom and stacked over the N channel transistor. Interconnect from the N channel from the top and P channel from the substrate backside, buried power rails. This is the latest device architecture which is in manufacturing. And again, the problem associated will remain the same. There is no change in that, my dear friend. So far, abhi isko main chhod deta hu. What I would like to tell you is the end. Road is end? No. Road is not end. Always listen to the market requirement. What are the application, what are the segment, and try to find the solution for that. Spot different situations by the different tools. You can see the image. If husband come late into the night, different tools are waiting for him. He is having, so late, okay, very late, Balan is waiting. If you are married. If you are come drunk late, again Balan is waiting. And if you have lipstick on your shirt, you're gone, buddy. Okay. So it is something like that. You have to develop your innovation by yourself. It is not that a single tool can handle everything. Different tool can handle different things. System integration can land up in the packaging. And I am stopping. I think I am making you bored. Leave it. So now what are the opportunities? The opportunities in front of us that government has started the business to support the manufacturing house in India. And under this program, our Honorable Prime Minister has, made out the policies, not in the short term, for the long term, to support the manufacturing hub in India. And mighty as ISM, we are the implementing agency. And what we have done so far, we have grown a semiconductor integration ecosystem in India by support of the government initiatives. You see different companies who have set up the system integration plant here in India already, which are manufactured and being pumped by the government of India. Lot of jobs opportunity as a system integration, embedded design, system designers are available in these domains. And government has given 50% of the capex investment. Central government is giving. If you want to set up a manufacturing facility in India, we are giving 50% of capital investment. If it is $3 billion, 1.5 central government will fund. Then there are the state governments who are giving 25% or and above what central government is going. So 75% is total capex investment is being consumed without having a stake by the governments, center as well as state. With these policies, 5 projects has been approved already, which are in progress. One is Tata with a fab having 28 nanometer technology node to 110 nanometer technology node of a wafer fabrication capacity of 50,000 wafers start per month. It is going to set up in Dhulera. The total cost of the plant is $11 billion. Out of this, 6 billion will be given by Government of India. And then we have the capacity 28 to 110 nanometer. It is going to be established in Dhulera, Gujarat. And then we have Micron, which is well known in the memory domain. And they are setting an OSAT plant with 2.7 billion investment at, again, Sanand, Gujarat. Tata is setting up an OSAT facility, packaging facility. They will get the wafers, which is manufactured from their customer, and dice it, package it, and give the product to them. So that's what the Micron Tata is setting, but in Assam, Moregaon. And this CG Power and Kins, they are again set up in Sanand, Gujarat. They are also OSAT facility with having a capacity of $0.9 billion, $0.4 billion, something like that. Okay, so with this investment, a lot of job opportunities to explore your potential in the domain of VLSI manufacturing is available. What requirement of the manpower is almost 85,000 direct skilled labor who is going to be employed in these facilities. So you do have the opportunity, to learn the technology. And of course, from where the technology is coming, all this technology is coming from their technology partner abroad. As I told you, big risk. To bridge the gap, we have to go for the R&D innovation roadmap to understand and absorb the technology, make the technology our own, so that any troubleshooting, if required in future, which must always be, you can do that. And of course, if any validation and improvement of the technology is required, until we know the nitty-gritty of the technology, we cannot improve that. So, and ecosystem case study means Gujarat has developed area, Noida has developed area. Gujarat has developed Dhulera as a semiconductor ecosystem. At Yamuna Expressway, UP government has developed area where 2 plants which are very recent, maybe in few months of time, government may announce those to be here. Okay, and many more are to come. So that's what the inputs are. We have signed the MOU with the US, with the Japan, with the Singapore, and with the European Union to collaborate on R&D, skill development, and material and ecosystem development in India. Applied Material, AMAD, Microchip, and Lab has established their R&D centers with the help of Government of India in India. They are the world leader in technology or equipment part. So they are having already a presence in India. This is how effort are being put by the government. Now ownership lies on all of us to take it forward for growth of our nation. Government has done its job. It's now our job to deliver them. So that's all. With this, thank you and Jai Hind.
Thank you, sir. Thank you, sir, for sharing such deep insights into the semiconductor industry. Your words have truly enlightened us. If any of the students have any questions, this is your platform. You can ask, sir. Any faculty members or any students who would like to know a little more from sir, would like to ask a few questions?
Where do we stop? So we are shrinking the size. Where do we stop?
Wavelength.
So what also means how many nanometers?
There is always a trade-off. The end of the road is not the end of the road. So far the shrinking is concerned, there's two limitations which I told my dear friend. If the device architecture is not being supported by the performance of the transistor, which is going to ultimate limit at 18 angstrom itself. Light cannot go beyond that. That's why wavelength I put, it will be very important. It will remain in touch with you. Okay, we are using 13.5 nanometer wavelength of light to explore, to resolve the features with the quadruple lithography process, which is very more technical to make you understand on that. But just understand, if you want to stitch a 0.01 micron line at say what structure I have told you, you have to expose 4 times in a single area. Etch and develop, etch, develop, etch, develop. And then only one part of a structure out of 2600 processing step has happened. If anything goes wrong there, your whole process is off. Light is the limitation. The laser source which we are using 13.5 nanometer, most of the case 3.5 nanometer will also work, but it is under development. If 3.5 nanometer comes, the cost is so high. Let me tell you, the scanner, which is the heart of the technology, means the exposure unit or a camera or the lithography, the cost of that machine is itself around $700 million, one machine. And this one machine comes in how many cargoes? 7 cargoes. This is the giant machine, okay? So complexity you can understand then thereafter. Even if you go to shrinking further, definitely the cost of ownership of the technology also should be viable so far as the commercial solution is concerned. There are the 2 factors only, whether the channel exists to make as a transistor. What does this require? At least one silicon atom between source and drain to make it conductive. If no silicon atom, you cannot make the conduction. So no transistor. Physical limit. Same is the physical limit with the light. Either I can resolve the structures which are closest to each other in the 3 domain, which CPP, one of the slide was mentioning, is 14 nanometer today. It will go worse to 8 nanometer only. If that CPP is not able to resolve the 2 lines which are 8 nanometer apart, I cannot do the technology. Let me tell you. Thank you. Anything else? कुछ पूछना है? हाँ जी मैम.
Maybe 10,000.
Sorry.
Why are we so focused on silicon and GaN? We can use graphene as well.
Yes.
Because उसकी mobility ज़्यादा है और आपने उसी पे बात करी that
बिल्कुल.
mobility is needed.
That's what actually I told you, the substrates are different, which slide I have skipped in this. Even see the mobility in the gallium arsenide, compound semiconductor. In GaN, they are very high as compared to the silicon, which is 1450. And in GaN, it is particularly around 2000. And if you talk about the silicon carbide, the mobility of the carrier is around 8500. Still high.
But in
And when you talk of the graphene, I'm coming to that, it is around 10,000. Now, where is the limitation? Whether the process of the material is integrable in making the device. That is the challenge. Graphene making as a conducting layer is now being explored to make as a conducting lines, not as a channel of the transistor. we try to make out the channel as a MOS structure out of the graphene. We cannot find a suitable insulator material which can give you semi-insulating properties to make source and drain. Of course, gate is conducting, which is graphene itself. So that's the limitation. But graphene can act as a conducting, replacing the copper as a back end of the line, seeing its mobility and conductivity and thermal properties.
But there is a limitation of it as well, because
Yes.
the band gap is 0.
Band gap is zero, it's a metal only. It comes between metal as well as in semiconductors. So metal only having a best property than the metal because its skin depth is very less. As compared to the skin depth, there is no resistance at all. So RC delay will be less when I am using the graphene as a material. As an interconnect, I am exploring, because since I cannot make semi-insulating to control the source and drain, that's why exploring it for the transistor won't be so easy. But of course, I can increase when the physical limitation of single atom silicon will seize the channel. I will put graphene in there. That's the point. Yeah. And that's what the researchers need to do right now.
So there is a saying that if you only improve in the wax making technology and you can improve on candle, you cannot make a bulb. So do you think that if we are heading literally towards an end of the technology, can we look at other technologies or the other materials? For example, maybe a quantum, which could be our new path.
Certainly, sir. That's why the material which I have shown in between end of the road, the material options are there, where the product and technology is available nowadays, and we are not stopping out there. As ma'am said, the graphene is an interconnect material which is being explored. It is not going to seize the technology at all. But definitely there is a limit while we are printing the device. But application has to be different. Another channel is, okay, I am not focused on the shrinking the device, but my two parameter, performance and area, is meeting, which comes to system on integration. That is coming to the packaging, heterogeneous package. In a unit area, I am combining different ICs in the packaged to give the optimal performance rather than shrinking the device, which is not even met by the silicon or any other substrate. Solution is there. That is being adopted. That's why road end is not giving the one side, but of course the three sides of it.
Okay, thank you, sir. One difficult question, sir. Which of these stocks are to be looked after in the future?
Which of these?
Stocks. Stock markets.
In semiconductor, I would say.
Yes.
I should remain silent. I am not expert of that.
That's why I said the difficult question.
Anyone else? Any more questions? Sorry, sir, we engage you a little more. There's one more student who wants to. Sure, sir.
Yeah.
How can I do that?
क्या बोले?
So I'm asking, if I ever wish to work with you personally, how can I connect with you?
I'm not a R&D manager right now. If you would have been in touch with me 6 months back, I would help you. But I can connect you with the right persons to whom you can work with.
Okay.
That is I am in administrative and policy making right now, advocating, implementing the policies of Government of India. But I can connect you to the right persons. So straight away always. Thank you. Yes, ma'am.
I think one last question, and I think we'll close the session after that.
So the main disadvantage is that it is very flux and it requires a very high
request
temperature
the other students to
fabricate,
please
around
maintain
1000 degrees
silence.
Celsius, and a clean room fabrication. Other countries are going towards emerging technologies, like you can say carbon nanotubes, thin film transistors. So why not India? Like we are not having any particular that PDK files for this thin film transistors, but you can see in UK and Korea there are a lot of more research going on in those thin film transistors, and here also IIT Kanpur is only one institute who is doing in thin film transistors. So why not India when it has lot more advantages as compared to CMOS technology?
TFT is used for the display, one thing.
Yes.
It is not for the process and all. What we have discussed for the process, ICs, as well as compound semiconductor power device, discrete. That was the focus of the today's talk. TFT is being used for display.
Yes.
And TFT have LCD, liquid crystal displays, OLEDs, organic LEDs, particularly AMO LEDs, and then we have micro LEDs. The technology remains with that is the manufacturing which is being utilized for making the CMOS device. Means basic patterning technique, lithography technique, and processing technique. This is being done on the glass. Then the back driver will again remain the CMOS, driving the screen. This screen is having the TFT on the back side,
Yes.
front side, and the back side it is having the control circuit. Control circuit is totally based on the CMOS technology. TFT is well matured. And why India? As I told you, ma'am, there is no such facilities so that the R&D, at least on the prototype level, can be matured. That's why we were lagging behind always. And there was no investment in that.
Sir, actually, you were saying about just the LED TFTs is nowadays used in variables also,
Yes.
and also in smart grids.
In
and smart
variable, it is
cities
not
also.
TFT. In variable, it is OLED. Okay, it is in variables because TFT is having higher power consumption as
Yes.
compared to the
Yes.
AMOLED and OLED.
So, but researchers are going on in wearable biomedical devices and
Yes.
also smart grids, smart
Yes.
cities.
Yes.
If we are dealing for the smart cities, there also we require flexible.
Certainly.
So, like in militaries also, we require some flexible chips. But
Yes.
CMOS does not provide that
The
flexibility.
CMOS will act as a driver for those LEDs.
Yes.
Okay. Those LEDs acting as a pixel only. They are acting as an imaging device. But these imaging device, see, you have to do the contrast, you have to do the imaging, you have to process the pixels also. That is the CMOS at the backside, always. Okay. And the TFT is the technology only for making the display board, only board. It is making a glass. Over that glass, we have made the TFT thin film transistors, whether it is LCD based or OLED, AMOLED based or micro LED based. All these are the TFTs. All these are the TFTs. They are placed onto the glass.
Yes.
Then they have to interconnect to the power source.
source.
That interconnect is being done by the CMOS drivers,
Yes.
which is called the driver. And then you have to put an address over it, which corner, which pixel is to be illuminated and how much, depending upon the feed of the image RGB at the back end side. And that RGB will give you the resolution. So in India, we are good in making the design of that. Because of not availability of the manufacturing infrastructure, so that we can create the TFTs, demonstrate that. Effort has been done, as you rightly mentioned, in the IIT Kanpur and even at Siri Pilani long back in 2007 to make the micro LEDs or GaN-based LEDs at that moment, but that remained in a very primitive stage. The time which we took in evolving the technology, world is 10 times faster. One is this drawback. I don't know what is the reason. Reason best known to us. I am knowing that though. I can speak being a government servant, but we know the reasons behind this. But we are at this moment we are trying to remove all those reasons, and if we are successfully able to do that, which is the target, definitely things will improve and you will have your own technology in your hand. That's why I was encouraging everybody why we need to learn the technology. Even if we are absorbing the technology, we have to master it by ourselves. Until unless we cannot, even if it is a simplex which we are talking about, the TFTs and LCD, which is having only 12 to 13 masking layer.
Yes.
Very simple
Very
technology.
simple technology.
But the back end side, but the front end, from front end side, but the back end side of this aspect, the CMOS again. If driver we have to come from outside, then again there's no solution. Only the problem is this: can we really bridge the gap right now? World is already, I think, I would say, one light year ahead in terms of technology. Light year ahead.
Yes.
There's no two ways. Whether we learn the technology from them, then start from there, it's up to have it the next jump. This is what we are adopting right now. But this has to be in a true spirit, where industry has to come forward to fund the R&D, to tell the students, to tell the researcher, to tell the faculty, this is my real problem. Give me the solution. I'll give the money. but in a time-bound manner, which is 1.5 years or 6 months. That's all. Today, in the past, what we have done, take a project, take it around say 10 years to develop the project. By that, world is already 50 years ahead. That's only the problem, nothing else.
Thank you, sir.
Thank you so much, sir, for sharing such deep insights into the semiconductor industry. Your words have truly enlightened us, and we are honored to have had the opportunity to learn from your vast expertise. As we come to the close of the event, I request respected Vice Chairman, Sir, Mr. Vineet Watts, and our revered DG Ma'am, Professor Amita Dev, to kindly felicitate Dr. Hooda by presenting him with a shawl and a portrait of Swami Vivekanand. I request Deputy HOD, Dr. Anand, to also join in for the photograph. निशिता इधर ही आ जाओ.
यहाँ मुझे बुला के